Welcome to this series of lessons. In our course content, we are going to discuss mechanical energy conservation. We are going to talk about also mechanical momentum and impulse, collision in one direction or one dimension, also collision in two dimensions. So at this point, I presume that we have learned what energy is, and we're going to deal with only one special type of energy, which is mechanical energy, which is simply the energy that includes both kinetic energy and potential energy. So in the law of conservation of mechanical energy, it states that the total amount of mechanical energy in a closed system is a key point. In the absence of dissipative forces, another key point, like friction and air resistance, remains constant. So the closed system is a system where there is no external interaction. So in such a system, we don't involve external interaction. So for example, we throw a ball upwards and there is no interference with it. Or you drop a stone from a height and it falls or lands on water. There is no any other force that is involved that comes externally and touches that system. Then that's a closed system. We have included absence of friction and air resistance. Friction and air resistance work almost in the same way, because as a system is going in a certain direction, these forces try to oppose the motion, therefore causing the system to lose part of its energy. So in that case, when the energy is lost, this is mechanical energy. For example, part of its potential energy or part of its kinetic energy is converted into heat, which is not mechanical energy. So in that case, the total system, total mechanical energy is not going to be the same, because a fraction of it has been changed into another form of energy, which is not mechanical energy. So this also means that the kinetic energy can become potential energy, or potential energy becomes kinetic energy. I give an example. If you drop a stone from a height, before you drop it, it is stationary, therefore it has only potential energy. But when you drop it, it starts to gain velocity, therefore it gains kinetic energy. So because our reference point may be the ground, so as it continues to go further to the ground, it is losing the height from the ground, therefore its potential energy is reducing and the kinetic energy is increasing. By the time it hits the ground, it's going to hit it with maximum velocity and zero potential energy. So that's an example of conservation of mechanical energy. So that's why in the same manner we have an equation here, which is used to explain the work energy theorem. For example, if we drop a stone, if we take the same example, drop the stone from a height, gravitational force does work by moving that object or that stone downwards. So that work which is being done is converted into kinetic energy. That's why the work energy theorem states that the net work done on an object is equal to the change in kinetic energy of an object. Therefore, if we had an object that has kinetic energy k naught initially, and then it's given velocity such that its final kinetic energy is k, then the work which is being done is simply the difference between the two kinetic energies. The other equation that we can think of is, if we, as I've explained before, if we threw a stone or any kind of object downwards from that height, if it has height h naught, it has potential energy mg h naught. And also because we have thrown it, we have given it initial velocity v naught, therefore it has kinetic energy a half mv naught squared. So as it goes, imagine at a certain instant it has gained a height hf, therefore at that height it has mechanical energy equal to the sum of potential energy, which is mg hf, and also kinetic energy, which is a half mv f squared, where vf is the final velocity at that point. So these are the equations that we are going to deal with in the next examples. We have the first example says that Jonah shoots a ball vertically upwards with a speed of 48 meters per second. What is the using the principle of conservation of energy? In this case, we are going to base on mechanical energy, find the height, find how high it rises. Okay, So let's dive in and see. If we have this ball initially at position A, then it is thrown vertically upwards with a velocity of 48 meters per second. We know that it will rise until it reaches a height where it can't go beyond, which we call maximum height. So at point A, let's say the maximum height is at point B. At point A, it has no height above A, therefore it has zero potential energy. But as it goes, it gains potential energy as it loses the kinetic energy. Therefore, here we would say that the potential energy, or probably we would start with kinetic energy. So the kinetic energy, or we call it K, which is lost, is equal to the potential energy which is gained. So potential energy is gained at A, but the kinetic energy was originally, potential energy is gained at B, kinetic energy was originally maximum at A. So kinetic energy is going to be a half mv squared equal to potential energy, which is mgh. In this case, is going to be h maximum. So they are saying how high will it rise? Therefore, in this case, h max is going to be equal to, you can realize here that the mass is useless. Therefore, this is going to be equal to u squared. It's going to be equal to v squared, velocity of projection, over 2g. If we feed in, it's going to be 48 squared divided by 2 times 9.81. If that's our acceleration due to gravity, then h maximum, how high to rise, is going to give us 117.4 meters. So we are using basically principle of conservation of mechanical energy. So that's the approach we use. Second example, Heskey drops a stone from a cliff at a height of 117.4 meter above the water level. Calculate the velocity with which it hits the water. So in this case, it's the reverse of the first equation. First question is dropping. Dropping here means that the velocity is zero. The initial velocity of the body is zero. So since it is zero, we have only potential energy at that point. So the potential energy at point A, for example, should equal the kinetic energy at point B. So the same equation works. mgh is going to be equal to a half mv squared. A half mv squared. Okay, a half mv squared. mv squared. In this case, we are looking for the velocity v, so it's going to be 2gh under root. If we feed in, it will be 2 times 9.81. If that's the acceleration due to gravity, times the height, which is 117.4, and the root v is going to be exactly the velocity in the first example, 48 meters per second. So we are using only the principle of conservation of mechanical energy.